This is my ALU Explorer. The 4 green LEDs and the 4 red LEDs represent the A and B inputs. The red LED in the top right represents the A equals B pin, and the green LED represents the carry out pin. The switch bank on the left holds the 4 select pins, the mode pin, and the carry in pin. I also have all 4 select pins, the carry in pin, and the mode pin sent to Arduino Nano, which decodes these inputs and displays what operation you're doing on an LCD screen. By putting all select pins on high and the mode on high, we've selected logic mode and F equals A, where the output is always equal to the A input. Now, by putting all select pins to low and keeping the mode and carry in the same, we can achieve the A equals not B. This is where the output is always equal to the inverted A input, as seen here. Now, by making the select pins high, low, high, high, we can achieve the function A and B. This is just ANDing each bit of the A and B input and displaying the output on the F0 to F3 pins. Now, by making the carry-in high, when it's active low, means there's no carry-in, and mode low to access arithmetic operations, and then making the select pins high, low, low, high, we can achieve A plus B, where it's just a classic adding A and B. Another key thing seen here is the green LED in the top right. This green LED is the carry out, and this only goes high when there's an overflow and acts as essentially the 5th bit. Now, by making the carry in low, we activate the carry that usually would be coming from another ALU in an 8-bit or 12-bit process. And this essentially just adds 1 to the output. As seen here with A plus 1, whatever A is, the output is just 1 more than that. Finally, by setting mode back to high and carry in back to high as well, and by setting the select pins to high, high, low, low, we achieve a very important function in the ALU. This is the F equals 1 mode. This mode essentially makes all outputs high no matter the inputs all the time. This is very important because, as seen by the single red LED, which indicates the A equals B pin, this pin only goes high when all outputs are high as well. We can use this in conjunction with the program counter's load function to achieve go-to and branching functions. So this is wired up. So here's the EEPROM, ALU, program counter. Top 4 bits of the program EEPROM go into the function pins of the ALU. Bottom 4 wires go into the input of the program counter. The A equals B pin with the open drain pull-up resistor goes down into this transistor inverter. So when this is high, the load pin is low because it's active low, so I need to invert it. And then I've also I put the firmware code onto the EEPROM, but I've made the first line 00 instead of 82, so because you see when it restarts. So right now it's at 0, so the output is all 0. But when we go to the first line, seen here, we have 0, 0, 0, 1, 0, 0, 0, 0. So this is the bottom 4, and this is the top 4 outputs of the EEPROM, which is good. Then we go to the next line, we have this, which is just 2, 1, which looks good. And then we go to the third, as we see here, 62. And then we go to the last one, C0, seen here. These two, the high, high, low, low, if you remember, that equals the F equals 1, which makes the A equals B pin go high no matter what. It comes down here and turns this LED on. It activates the load pin right here. And seen here, since these are all zeros, because it's C0 instead of C1, 2, 3, whatever, since these are all low, then on the next clock cycle, the program counter, since the load pin is low, will take whatever's here, which is just all zeros, and put that onto the count. So it will go to 0. So now this thing will only count up to 5. And then it will restart. And this is how we can use the A equals B pin as go-to functions, because instead of C0, I could have put C3 or something like that, and it would have changed what this line would go to. And yeah, so this is how that works. Yeah, so that's how you can use the A equals B pin to achieve branching